What about our tomorrow session? We will be attending tomorrow's physics session, right? Do you have exam on this Sunday? You don't have it in month. You don't have that. I hope you can see the board. Can you see the board? Okay. Okay, and what about the sound? Is the sound clear? Okay. Okay. What are we actually? What did we discuss the last time? The equation for solenoid, maybe? No. The force between two parallel lines. Huh? The force between two parallel lines. We discussed the force between two parallel lines as the last one, right? The force between two parallel lines. What was the force between two parallel lines? If you have two parallel lines like this, and the value of current is directed in upward direction. Value of current is directed in upward direction. If this is the current, you can use the right hand thumb rule. If this is the current, and encircling fingers will be the direction of magnetic field. So the magnetic field will be like this. Can you imagine that? Circular magnetic field. So the magnetic field will be circular. It is coming from here. This is magnetic field line, and this is coming from here, and it is entering here. Okay. So the magnetic fields are entering like this. This is the direction. And if magnetic field is entering here, this is like this. Magnetic field is entering the B. This is A, this is B. Entering B here. I cannot draw this magnetic field, so I am drawing it like this. This is magnetic field. Okay? Like that. This is a current which is going upwards. So I have to put my thumb in the upward direction, and the encircling fingers will give you the direction of magnetic field. So magnetic field will be from here to here, like circular magnetic field. So the magnetic field here will be circular. Okay, and it is entering the conductor A like this. Entering conductor A like this. Entering conductor A like this. So the magnetic field is acting outwards. And this is magnetic field due to A, and this is magnetic field due to B. Okay, this was the and what was the equation? If AB was equal to but opposite of FD. If AB was equal to but opposite of FBA. We got that. Right? So this is it. And we change the direction of current. If we change the direction of current, this is in the same direction. This is now parallel currents. Parallel currents. This is now parallel currents. And this is what? This is. Now we are drawing anti-parallel currents. They are in opposite direction. They are in opposite direction. This is A and this is B. Now the currents are anti-parallel. Now the currents are anti-parallel. Currents are anti-parallel. Can you understand that? Currents are anti-parallel. If currents are anti-parallel, the BA will be exactly similar to the above. BA will be similar to the above. So BA will be like this. BA, that's magnetic field due to A. Magnetic field due to A will be in that direction. And look at the current in B. Current in B is in downward direction. So you have to put your thumb in downward direction. And the current is like this, and magnetic field is like this. Magnetic field is, the direction of magnetic field is given by encircling fingers. Encircling fingers. So magnetic field is from here to magnetic field is from here to here. So it will be like this. It's also entering into A. It also entering into A like this. It is also entering into A. I cannot draw that. I cannot draw the magnetic field that is entering into A. Okay, so I am drawing it like this. This is magnetic field due to B. This is magnetic field due to B because the direction of current has changed. Okay. What about the force direction here? Force direction. Force direction will be given by Fleming's left hand rule. So force direction will be given by Fleming's left hand rule. Got it? Okay. Then stretch the 3 fingers in perpendicular direction. The 4th finger will show you the direction of magnetic field. So the magnetic field is like this. For A, the magnetic field is like this. Okay, magnetic field is like this. Current is in upward direction. So current is like this. And force is towards A. I will use another color. Force is towards A. Force is towards A. Right? Like this. Force is towards A. Okay? Then force will be towards A like this. This is FBA. This is FBA. Force on B due to A. That's FBA. Force on B due to A. Force on FBA. Force on B due to A. Force on B due to A. Okay. What about force on A due to B? Force on A due to B. Due to this magnetic field, there will be a force. How can you find the direction of that force? How can you find the direction of that force? Fleming's left hand rule. What is the direction of magnetic field? Now magnetic field is outwards. This is the magnetic field. That magnetic field is outwards. So I have to hold my finger like this. And what is the direction of current? Current direction will give you by the middle finger. So the current is like this. And this is what force. Thumb will give you the force direction. So force is towards me. Force is towards me. I'll show you that. Force is towards me. Force is towards me. So this will be the direction of force. And it is force on A due to B. Force on A due to B. Okay? So when you are applying the same direction like here in anti-parallel current, what you will get? What you will get? This is the direction of magnetic field. And what is the direction of current here? Current is in the upward direction. Okay? Structured thumb will give you the direction of force. So the force is outwards. Force is outwards. Okay? Then the force is outwards. Force on B due to A is away from A. Or away from A. It is away from A. It is away from A. And what about here? Magnetic field is entering here. And current will be given by the direction of the middle finger. This is the direction of current here. And force will be given by the structured thumb. So force is away from B. Force is away from B. Force on A due to B is away from B. Away from B. Away from B. Now look at it. These are attractive. These are attractive forces. So the force is attractive here. The force is attractive here. And what about here? The force is repulsive. Here the force is repulsive. Here the force is repulsive. Did you understand that? Here the force is attractive and here the force is repulsive. This was the last topic we discussed. And now I want to show you what is the definition of 1 ampere. Definition of 1 ampere. What is 1 ampere? Okay? And you can find the definition of 1 ampere using this idea. Take one pair of parallel wires. Take one pair of parallel wires and they are at a distance of 1 meter in space. You are placing the two parallel wires in the space and between them there is a distance of 1 meter. Between them there is a distance of 1 meter. And if the currents that is passing through it, you have to find the current passing through it. And what is the equation? Previous equation that between the equation for force that between both of them. What was the equation of force that is between both of them? BIA. This is BIL sin theta. This was the equation of force. Okay, BIL sin theta, and we have B here. We have B here. You can use any of that. You can use any of the equation. Any of the equation. How was B? How was B in the previous one? You know I by 2 pi D. That is the equation for B. So mu naught. If this is A, this is B. BA. We will talk about BA. This is BA. Then what is BA? Mu naught IA divided by 2 pi into 2 pi D. 2 pi D. And into this is B and I, which is the current causing the force. Which is the current causing the force here. IA or IB. This is IA and this is IB. Which is the current causing the force here? Now that's IB. IB is the current causing the force here because a current carrying conductor in a magnetic field will experience a force. Okay, the magnetic field is produced by this current, but the force experiencing on this B is due to the current through B. The current through B. So the current through B is causing the force. Current through B. So that will be mu naught IA IB L into sin theta. What is the theta here? Theta. Yeah. Theta here will be 0 because magnetic field is entering the wire in 90 degree. Magnetic field is entering the wire in 90 degree. So theta will be 90 degree and sin 90 will be 1 and force will be BIL. Okay, so you have to put just this is BIL. This is the force. And if they are asking for 1 ampere, definition of 1 ampere, draw this figure and write this equation. Draw this figure and write this equation. And then take some conditions. Assume some conditions. Assume some conditions. The conditions are if IA is 1 ampere, if IA and IB are 1 ampere, IA and IB are 1 ampere, and L is the length. L is 1 meter. L is 1 meter. And what about D? D is the distance between them. Distance between them is also 1 meter. Distance between them is also 1 meter. Hello? Okay. Look here. Look here. This is the force. This is the equation for force. And what if instead of taking L is your 1 meter, you take force per unit length? If you are taking force per unit length, what will be the equation of that? Force per unit length. Force per unit length. What is that? Force per unit length. Yeah, force per unit length. Force per unit length. I can take it as F4. I can take it as F4. Then force per unit length will be F by L. Force per unit length will be just F by L. If you are taking force per unit length in this equation, what will be the value? This L will be gone. There is mu naught IA IB L divided by 2 pi d. So this L will be gone from the equation. That's F by L. Now this is a new term. What is that new term? That's force per unit length. Now we have to see this force per unit length. Force per unit length, mu naught into what is IA? Value of IA is 1 ampere. What is the value of IB? That's again 1 ampere divided by 2 pi into 1. Because D is 1. Because D is 1. Right? Okay. Then you can, if you are not remembering this, you can also use the equation, also use the condition L is equal to 1. Then also you will get the final value, but this will be the equation. That will be the equation of force, not the force per unit length. Okay, so the definition has to be changed a little bit. Now take this force per unit length, you will get the correct definition for 1 ampere. Because 1 ampere is what? 1 ampere is a fundamental unit. Current is a fundamental quantity, and 1 ampere is a fundamental unit. So you have to define it. The definition is like this. And if you are doing the calculations, what is the value of mu naught? What is the value of mu naught? Mu naught by 4 pi. Mu naught by 4 pi is 10 raised to minus 7. Then what is mu naught? Mu naught will be 4 pi into 10 raised to minus 7. Right? That's the value of mu naught. If you are giving the value of mu naught here, what you will get? If you are giving the value of mu naught here, what you will get? Force per unit length is equal to mu naught is what? Mu naught is 4 pi into 10 raised to minus 7. 4 pi into 10 raised to minus 7 into 1 divided by 2 pi. Now this pi is gone, and 4 and 2 can be cut. You will be left with 2 into 10 raised to minus 7 is the force per unit length. That's not force. That's force per unit length. So the unit will be Newton per meter. The unit is not Newton. The unit will be Newton per meter. Okay. Now you can define what is 1 ampere. Now you can define what is 1 ampere. Then tell me what is 1 ampere. 1 ampere will be the current that is passing through parallel conductors in space, having a distance between them as 1 meter, and they are experiencing a force per unit length of 2 into 10 raised to minus 7 Newton per meter. If you have 2 conductors and there is 2 equal and same direction current is passing through that conductors, there will be a force per unit length of 2 into 10 raised to minus 7 Newton per meter between them. Then the current passing through them will be 1 ampere each. Did you understand that? You don't have to study that by heart. Just study this idea, and you can reciprocate that into words. You can reproduce that idea into words. What is that? If there is 2 parallel conductors through which the current is in the same direction and they are in space, at a distance of 1 meter, and the force per unit length between them is 2 into 10 raised to minus 7 Newton per meter, then the current through each will be 1 ampere. That's the definition of 1 ampere. Did you understand that? That's the definition of 1 ampere. Now we will be looking at the equation of force. Do you have to write this? Or do you have a note of this one from the school? Very right. Yeah, this is it. This is the equation. If 2 currents are in the same direction, there is no branching. That's all. This is our note on school. Under the law, application of Newton's law. Okay. Completed? Okay. Now we have to see the equation for torque. Equation for torque. So, this is a current carrying conductor in a uniform magnetic field. This is a current carrying conductor in a uniform magnetic field. And I am naming it A, B, C, D. I am naming it A, B, C, D. Just look at AD and BC. AD and BC are parallel to the magnetic field. The equation for force is what? The equation for force is BIL sine theta, right? If L and B are parallel to each other, then theta is equal to 0 and there will not be any force on AD and BC. Right? But what about AB and CD? Yeah. For AB and CD, theta is equal to AB and CD, theta is equal to 90 degree. AB and CD, theta is equal to 90 degree. Theta is the angle between magnetic field and length. Magnetic field and length or vector L. Vector L has same magnitude as that of I and the direction of I. Sorry, length has vector L has the same magnitude as that of L. Magnitude as of length. Magnitude as that of length and direction in the direction of current. Direction in the direction of current. So I'm taking the current direction like this. This is the direction of current. So this is the direction of current here, and current here will be like this. The direction will be like this. Okay. So for AB and BC, theta will be here. Theta is 0. Same direction is here. AD. Here in the case of AD, theta will be 180 degree. Then sine 180 and sine 0 will be 0. That means there will not be any force on BC and AD. No force on BC and AD, but AB and CD has the angle 90 degree. Angle 90 degree. Then what is the equation of force? Force will be BIL. Sin 90 is what? Sin 90 is 1. Sin 90 is equal to 1. So the force will be BIL. The force will be BIL. Okay. If I am looking at any lines, AB or CD, I am taking the breadth curve. What is this? This is the breadth curve. If I am taking the breadth, you can use Fleming's left hand rule here. You can use Fleming's left hand rule here. This is magnetic field. What is the direction of current? Direction of current is here, and force is inwards. Force is inwards. So I am drawing that force, inward force. This is force here. This is force here. This is force here. The force is inwards here. Okay. What about force on the other side? What about force on the other side? Magnetic field is in that direction, but current is in this direction. Force is outwards. So force here is inwards. Force here is inwards, and force here is outwards. Force here is outwards. I can draw it like this. So what is this? Equal and opposite forces. They are equal and opposite forces, and they are not collinear. if there is an equal and opposite forces acting on a body and they are not collinear, it will create a couple. It will create a couple. It will create a couple. Due to this couple, there will be a rotation of this coil. Due to the couple, there will be a rotation of the coil. Due to the couple, there will be a rotation of the coil. Okay, due to the couple, there will be a rotation of the coil. And look here, what defines the rotation? What defines the rotation? Torque is the one that defines the rotation, right? Torque is the one that defines the rotation. So I am making it too much torque. Okay, I can simply write the equation of torque and skipping all the statements. Okay, torque is what? Torque is defining the rotation. It is the turning effect of force. Torque is the turning effect of force. So torque has this equation: force into perpendicular distance. Force into perpendicular distance. That is torque. What is torque? Force into perpendicular distance. Only one force into perpendicular distance. So torque will be equal to force into perpendicular distance. What is the force here? Yeah, force here is VIL into what is the perpendicular distance between the forces? Yes, one force is inwards, the other force is outwards, and the distance between them is B, breadth. Right? The distance between them is B, breadth. So you can use B here, and you have L into B here. What is L into B? What is L into B? Length into breadth. What is that? Yeah. So tau is equal to this is DIA. DIA. What is torque? What is the equation of torque? Torque is DIA. Torque is DIA. Torque is DIA. Torque is DIA. This is the equation for torque. This is for one coil. This is for one coil. If there are n coils, if there are n coils, what will be the torque? N into DI. The equation for torque will be N into DIA. Equation for torque will be N into BIA. Got it? Now, this is the case if theta is 90. If theta has another value, if theta has any value, the torque, and skipping the small derivation part, and I will give you the equation. If the value of theta is not 90, if the value of theta is not 90, then the equation will be NBIA sin theta. There will be a sin theta also. There will be a sin theta also. If there is the angle between them is not 90 degrees, then there will be a sin theta also. So tau is equal to torque is equal to NBIA sin theta. That will be NBIA sin theta. Okay. Is there any topics with a heading circular current loop as magnetic dipole with you? Circular current loop as magnetic dipole. Circular current loop as magnetic dipole. Circular current loop as magnetic dipole. We have discussed that, right? We have discussed that. Oh, no. In mind. We have discussed the circular current. Yeah, circular current loop can be considered as a magnetic dipole. So what is magnetic dipole? Magnetic dipole is M. M is I into A. M is what? I into A. Okay. Now we are going to look at moving coil galvanometer. Very important topic. moving coil galvanometer. Moving coil galvanometer. Moving coil galvanometer. Just look at it. Moving coil galvanometer. What is this? What is the use of a galvanometer? To find or to detect very small current, the direction and value of very small current. That's moving coil galvanometer or MC galvanometer. MC galvanometer, moving coil galvanometer. To detect small value of current. To detect small value of current. To detect small value of current. Okay? We are using a concave shaped permanent magnets here. Concave shaped permanent magnets here. We are using concave shaped permanent magnets here. Okay. And what is the coils look like? I will simplify the coil. I will simplify the coil like this. I will simplify the coil like this. This is a coil. This is an aluminum frame, and there is insulated copper wire wound on that aluminum frame. Insulated copper wire wound on that aluminum frame, and there will be a phosphor bronze wire here. What is that? That's a phosphor bronze wire, and here you will have a spring stripper. Spring stripper. Okay. Current is entering towards the galvanometer like this and leaving the galvanometer like this. And we have studied in current electricity that galvanometer is always connected in series. Galvanometer is always connected in series. Did you understand that? Galvanometer is always connected in series. That means this is the current entering, this is the current leaving. Here the current is entering, here the current is leaving. Okay. So what is this galvanometer? Galvanometer is a device to detect small value of current. That's the first one. Then this is a concave shaped permanent magnets. Concave shaped permanent magnets. What is the use of a concave shaped permanent magnets? To direct the magnetic field perpendicular to the coil. To direct the magnetic field perpendicular to the coil at all points. Okay. The figure 4 coil in your note will not be this one. I am simplifying this. This is a figure 4 coil, and this is what? This is an aluminum frame. Yeah. Yeah. That's an aluminum frame. Yeah. There is an aluminum frame, and on that aluminum frame, copper wire is wound on it. On that aluminum frame, copper wire is wound on it. Right? I will cut short the derivation part. I will cut short the derivation part. Did you understand this idea? Okay. Now the current is entering like this. Current is entering like this. Current is entering like this. That means this is a coil. This is a coil. And current is entering into the coil through a phosphor bronze wire. This is a phosphor bronze wire. A phosphor bronze wire. What is the use of a phosphor bronze wire? We have studied that in 11th standard. Phosphor bronze wire has very high elasticity. It shows very high elasticity. So this is the direction of current here, and current will be going here and here. It is circulating like this. It is circulating through the coil and finally coming out of the coil. Current is entering the coil and it is circulating the coil. There is too many coils. There is too many turns, and through the turns, current is circulating like this. Finally, current is coming out. Finally, current is coming out through the spring stripper. Did you understand the structure, the construction? So just look here. What will happen here? This is providing a magnetic field. These poles are providing a magnetic field. The poles are providing a magnetic field. You can use Fleming's left-hand rule to find the direction of force. There will be a force acting on this. Just like we saw here, there will not be any force on top and bottom, right? Because theta is 0 and 180, there is no force. Here, what will be the same case will be here also. There will not be any force on top and bottom. The force will only exist here and here because the theta is 90 degree. Because the value of theta is 90 degree. Okay. So this is the magnetic field, this is the current, and force is inwards like this. Force is inwards here. So the force is inwards here. Force is inwards here. What about here? Magnetic field here. Current is in the opposite direction or current is downwards. Force is outwards. Force is outwards. Force is outwards. And what is this? This is the breadth. This is the breadth. This is the breadth. Okay. Due to the equal and opposite forces on vertical sides, equal and opposite forces on vertical sides of the coil. Vertical sides of the coil. Vertical sides of the coil. Equal and opposite forces on the vertical sides of the coil creates a couple. Creates a couple. Creates a couple. Equal and opposite forces on both the vertical sides of the coil creates a couple. What is the moment of couple? Moment of couple is torque. Moment of couple is torque. So due to this couple, this coil will turn. There is a force in this direction and a force in this direction. So the coil will turn. If the current passes through the coil will turn. Right? There will be a pointer on coil. There will be a pointer on coil. What is this? This is the pointer. There will be a pointer on coil. If the coil turns, the pointer will be moving like this. This is the coil. If the coil turns, this is the pointer. If the coil turns, pointer will move like this. Then the pointer will show you the direction of and measurement of current. The direction and value of small value of current. Right? Then there is a coil. There is a couple, and the moment of the couple or torque, I can call that torque as deflecting torque. There will be a torque produced. Okay? Creates a couple, a torque produced. I am writing the value of that torque, and I am calling that torque as deflecting torque. Deflecting torque, because this torque is deflecting the pointer. Because the torque is deflecting the pointer, so I am calling it as deflecting torque. Can you understand that? I am calling it as deflecting torque and torque. What is the equation for torque? What is the equation for torque? NBIA sin theta. This is the equation for torque. This is the equation for torque. And what is this theta here? Theta here is what? This is torque, NBIA sin theta. This is the equation for torque. And give me the value of theta here. What is the theta? What is the theta here? Theta here is 90 degree because magnetic field is entering the or crossing the length. Magnetic field is crossing the length at 90 degree. So theta is 90 degree, theta is 90 degree, and sin 90 is 1. Sin 90 is 1. Okay, so tau d is equal to NBI. Right? NBIA. NBIA. There is A also in this equation. Okay, NBIA. Not just sin theta, there is I also. A sin. And what is this? NBIA. NBIA. Right? You can call it as equation number 1. That's equation number 1. You can call it as equation number 1. Okay? And I just told you this is a phosphor bronze wire, and this phosphor bronze wire has high elasticity. This phosphor bronze wire has high elasticity. If the coil rotates like this, the forceful bronze wire twists. I will write it. The forceful bronze wire twists. Forceful bronze wire. Forceful bronze wire twists. Forceful bronze wire twists. If the forceful bronze wire twists, if the forceful bronze wire twists, there will be an opposite torque created in it. There will be an opposite torque created in it. This is the deflecting torque. Due to this deflecting torque, the coil rotates. Due to the rotation of coil, forceful bronze wire twists. Due to the twisting of this forceful bronze wire, there will be an opposite torque created in it. Okay, there will be an opposite torque created in it. Opposite torque created. Opposite torque created. There will be an opposite torque created in it. Did you understand that? Then I am calling that opposite torque as restoring torque. What is that? Restoring torque. I am calling it as restoring torque. Restoring torque. I am calling it as restoring torque or toe arm. Restoring torque or toe arm. Restoring torque or toe arm. Okay. You don't have to. You should study this by heart. Restoring torque has this equation minus C theta. Restoring torque has this equation minus C theta. C is a constant. C is a constant. It is called a torsion constant. What is the value of C? Torsion constant. Torsion constant. The name of C is torsion constant. It is the torque acting per unit angle. It is torque itself. It is torque itself and torque acting per unit angle. That's C. Torque acting per unit angle. Torque acting per unit angle. This is C. Okay? And if deflecting torque is increasing, this restoring torque also will be increasing. Right? Deflecting torque increasing, then the restoring torque also will be increasing up to a point when both of them becomes equal. Up to a point when both of them becomes equal. When both of them becomes equal, the deflection stops. When both of them are equals, then the deflection will stop. If the deflection stops, then deflecting torque and restoring torque will be equal at that time. Deflecting torque and restoring torque will be equal at that time. Then you can equate these equations. NDIA, this is deflecting torque. This is deflecting torque. And what is restoring torque? Restoring torque is minus C theta. What is that? Minus C theta. There will not be a minus because if you are adding both of them, you will get what? You will get a 0. You will get a 0. If you are adding deflecting torque and restoring torque, they will be giving you 0. The value is 0. If you are bringing that, you will get here BIA is equal to C theta. Because it is equal and opposite. Equal and opposite. Tau D is equal to tau R. But equal and opposite. That's why there is a minus sign in it. That's why there is a minus sign in it. It is equal and opposite of deflecting torque to show that there is a minus sign in it. And when you are adding them, you will get 0. When you are adding them, you will get 0. That means NDIA will be C theta. NDIA will be C theta. And I am finding the equation for I. What is the equation for I? That is C theta divided by NDA. The equation for I will be C theta divided by NDA. Equation for I is C theta divided by NDA. And we have said C is a constant. What is N? N is the number of turns, it's a constant. What is B? B is the magnetic field, and this magnetic field is produced by permanent magnet, so it is a constant. A, area is a constant also. So what is this? This is I is equal to a constant into theta. Right? It is I is equal to a constant into theta. C, N, B, A, these all are constants. These all are constants. If I is equal to a constant into theta, you can write it like this: I is proportional to theta. Right? If I is equal to C theta divided by NBA is our equation, and C and BA are constant, then you can write it like this: I is directly proportional to theta. What is the meaning of that? Theta increases. Yes. Or current increases, theta increases, current decreases, theta decreases. That means you can detect current just looking at the pointer. Right? From the deflection of pointer, you can look at the current. You can look at the current. Also, you can detect the current by looking at the deflection of the pointer. You can detect current. Current is proportional to deflection of pointer. Deflection of pointer. Current is proportional to deflection of pointer. Current is proportional to deflection of pointer. Did you get it? Current is proportional to deflection of the pointer. I am trying to make it very simple. Maximum. I'm cutting short all the details of it so that you can appear for the exam, school exams. We will take it detail. We will discuss this in detail in the coming classes. Okay, did you understand that? Moving coil galvanometer. Okay, this is an important topic, moving coil galvanometer. This is used to detect a small value of current. Or you can measure that also. You can measure the small value of current also. And this is what? This is N and S. What is N and S? They are permanent magnets and they are concave shaped. Why they are concave shaped? To get the magnetic field at 90 degrees. At always. At every point, the magnetic field on the coil will be 90 degrees. It will be entering the coil at 90 degrees. And this is what? This is an aluminum frame. There is insulated copper wire wound on it. This is called a coil. And the coil is suspended by a phosphor bronze wire. And there is a spring strip out of the coil. Okay? Current is entering through the coil through phosphor bronze wire and leaving the coil by spring strip. And galvanometer is always considered in parallel. Sorry, series of. And when the current is passing through the coil, there will be equal and opposite forces on the vertical sides. Equal and opposite forces on vertical sides of the coil. That will create a couple. That couple will have a moment of its own. That's turning effect of the force or moment of couple is called torque. That means there will be a torque created there, and that torque can be called deflecting torque or TOD. TOD has this equation NDIA sin theta. So you can use that equation NDIA sin theta, and theta is 90, sin n is 1. So NDIA. That's the deflecting torque. If a deflecting torque is created, the phosphor bronze wire will twist. Due to the twisting of phosphor bronze wire, there will be opposite torque created in it also. That opposite torque is called a restoring torque. So tau R is equal to minus E theta. C is called a torsion constant, and it is torque acting per unit angle. So you can add both of them and you will get 0 because they are equal and opposite. So NBIA will be equal to C theta. NBIA will be equal to C theta, and I is equal to C theta by NBA. C and BA are constants. So I will be proportional to theta. That means you can measure the value of current from the deflection of the pointer. From the deflection of the pointer, that is the theta. Okay? That is theta. Deflection of pointer is what? That's theta. Did you understand that? Okay. Now, our final topic here, that's conversion of galvanometer. Conversion of galvanometer. What is the use of a galvanometer? What is the use of galvanometer? To detect small value of current. What is the use of ammeter? To measure current. Ammeter is to measure current. The galvanometer is to detect small value of current. What if you are connecting a galvanometer instead of ammeter in the path of a large current? In the path of a large current, what will happen? It will not work, not just it will not work, it will damage, it will be damaged. The galvanometer will be gone, right? So you can convert this galvanometer into an ammeter. That's the first one we are going to study. Conversion of galvanometer into ammeter, into ammeter, into ammeter. You know what is ammeter? What is ammeter? Ammeter is the device used to measure the large value of current. Okay? And if a large value of current is passing through galvanometer, just look at the figure. What is this? Galvanometer is designed to pass very small amount of current. If a large value of current is coming through this galvanometer, it will be damaged. The coil will be burnt out. Okay, so we are using a small trick to convert this galvanometer into ammeter. How can we do that? That's very simple. This is galvanometer. You have to connect a small value of a resistor. A small value of a resistor of small value parallel to the galvanometer. You have to connect a small value resistor in parallel to galvanometer. You can turn this into an ammeter. It's that simple. And this resistance is called shunt resistance. What is the resistance called? That's shunt resistance. Shunt resistance. Who is this shunt resistance? Shunt resistance is a very small resistance. That's a very small resistance. Shunt resistance is what? That's a small resistance. Small resistance. Small resistance connected parallel to galvanometer. Connected parallel to galvanometer. Connected parallel to galvanometer. Parallel to galvanometer. Connected parallel to galvanometer. What is the use of that? To protect galvanometer from larger current or heavy current. To galvanometer, to protect it, to protect it from heavy current. Heavy current. How is that happening? How can this small value of resistance protect this galvanometer? Just imagine there is a large value of current passing through this line, passing through this cable. At this point, what will happen? Yeah, the current will be split. Current will split, right? The current will split, and a value of current will be going through this one, and also another value of current will be going through this. I am taking the current going through galvanometer as Ig, and I am taking the value of current going through the shunt resistance as Is. Then which is the larger current? Which is the larger current? Ig or Is? Which is the larger current? Of course, it will be Is. Why is that? It is the simplest path. Current will always choose the simplest path. This is having small value of resistance, right? So the current will choose that path. Current will prefer that path more, and there will be current through galvanometer also, but most of the current will be flowing through the shunt resistance. Did you understand that? Most of the current will be flowing through the shunt resistance. because current will choose the simplest path. This is the simplest path. So current will choose this path. Most of the current will be passing through it. So IS will be greater. IS will be greater than IG. This is how the shunt resistance is protecting the galvanometer. Okay? Okay. Now you can use the idea of parallel connection. If you have connected two resistances in parallel, the voltage will be same. The voltage will be same. And you have to find the value of current. You have to find the value of current using the galvanometer. How can we achieve that? The voltages are equal, right? Voltages are equal. Voltages are equal. Voltages are equal. That means what is the voltage that is across this galvanometer? Take the resistance of galvanometer as G. G is what? G is taken as resistance of galvanometer. Resistance of galvanometer. Resistance of galvanometer. Then give me the voltage across galvanometer. Yeah, current into resistance. That's the voltage across galvanometer. Current into resistance. Which is the current into resistance? Ig into G. Ig into G. Ig into G is the voltage across galvanometer. Did you get it? And it is equal to current into resistance here. Here the current is IS. So IS into S. IS into S. IS into S. Did you get it? IS into S. Now tell me what is the value of IS? What is the value of IS? IS will be yeah. No. I is what? I is what? I is the sum of these two currents, IG and IS. IG and IS. This is current I. I is IG plus IS. Did you get it? Okay. Then what is IS? What is IS? What is IS? IS will be I minus IG. IS will be I minus IG. Okay? IS will be I minus IG. So I will write it in the IG. G is equal to IS is I minus IG. I minus IG into S. I minus IG into S. So what is the value of S or the value of shunt resistance? You can bring the term to the other side. That means that will be IgG by I minus IG. IgG by I minus IG. Did you get it? IgG by I minus IG. Now this is the equation for shunt resistance. If you use the shunt resistance having this value, if you are using the shunt resistance with this value, you can measure the current. 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 Okay? Right? Did you understand that? That's a very simple derivation and very important one also. And now the second one. We can convert galvanometer into voltmeter also. Into voltmeter also. Into voltmeter also. We can convert galvanometer into voltmeter also. What is the use of a voltmeter? What is the use of voltmeter? Voltmeter is to measure voltage. To measure voltage. To measure voltage. Voltmeter is used to measure voltage. Okay. How can you do that? This is galvanometer. This is galvanometer. And voltmeter is always connected parallel to a device. Parallel to an element. If you want to measure the voltage of this resistor, you have to connect the voltmeter like this. You have to connect the voltmeter like this. Did you understand that? Now, if you want to convert this galvanometer into voltmeter, you can connect a resistance in series with the galvanometer, and the value of the resistance should be large. Okay. So by connecting a large resistance in series with the galvanometer, you can convert the galvanometer into a voltmeter. How can you convert galvanometer into voltmeter? By connecting a large value of resistance in series with the galvanometer, you can convert the galvanometer into voltmeter. Did you understand that? This is our idea. Okay. And this is what? This is the value of the current. This is the value of current. And the same current will be passing through Ig. And the same current will be passing through Ig. Is there any problem? Is there any problem? Why is that? Is there any problem with the galvanometer? Hmm? Why is that? Why is that? The galvanometer, what is voltmeter? Voltmeter is the device which measures the voltage, right? And the voltmeter's resistance will be very large. The resistance of the voltmeter will be very large, right? That means very small amount of current will be passing through this voltmeter. Okay, and we are using a very large value of resistance here also. So the current will be very small, right? The current will be very small. You are measuring the voltage here. You are measuring the voltage here. I am taking that as V or E. I can take it as V or E. I am measuring the voltage here. I am measuring the voltage here. So if you want to measure the voltage of some element, you have to connect this setup onto that element by parallel. Because voltmeter is always connected in parallel. If you have connected this setup as parallel, there will be very small amount of current that passing through this setup. Why is that? Because there is a large value of resistance. There is a large value of resistance. The current drawn from the circuit will be very low, right? If you have connected this thing, this setup, if you are connecting this setup parallel to the resistance here, this is the resistance. You have to find the voltage across. You have to find the voltage across, right? You have to find the voltage across this resistance. So you are connecting the galvanometer and the large resistance is set up like this, like parallel. If you have connected them parallel, this is a large value of resistance. Most of the current will be passing through this, and very small amount of current will be passing through this. Very small amount of current will be passing through that galvanometer and a large value of resistance. So the galvanometer will be protected. Galvanometer will be protected. It will not happen anything. Right? Okay. Now what is the voltage across here? The voltage across here is what? Voltage is current into resistance, right? Current into resistance. The current passing through here is what? Yeah, that's Ig. The current passing through here is Ig. Ig into what is the resistance here? Not just R. There is G and R also, and they are connected in series. They are connected in series. So you have to add them G plus R. This will be the resistance. V is equal to Ig into G plus R is the resistance. Okay. Okay. Then V is equal to what? Ig into G plus Ig into R. Ig into G plus Ig into R. You want to find the value of resistance. Then only you can construct this, right? Just like we found the value of shunt resistance here. If you know the shunt resistance, then only you will be able to construct this ammeter. Like that, you have to find the value of resistance, then only you will be able to construct this setup. So you want to find the R, the value of R. You are placing this Ig into R here. You are placing Ig R here, and you are bringing the Ig to the other side. What will be then? That will be V minus Igg. V minus Igg. Right? V minus Igg. V minus Igg. Right? Then what is the value of R? Yes, R is equal to V by Ig minus this is IgG divided by Ig. Now this Ig will be gone from the equation, right? Now the Ig will be gone from the equation here, and what you are left with? You are left with the equation for R. What is the equation for R? V by Ig, V by Ig minus G, V by Ig minus G. This is the equation of R. V by Ig minus G. V by Ig minus G. V by Ig minus G. Okay? This is the end of our chapter. This is the end of our chapter. Don't worry, I will take this chapter once again. During the regular class, I will take the chapter clear and sound, and I will dictate all the notes. I will give you all the notes that is concerned with this chapter and the topics. And every topics and every ideas, we will make it clear. Okay. Now, what you need? You need some calculation questions from this or the previous, right? What about tomorrow? Are you okay tomorrow to have a revision session or like?
Yes.
Will you be studying some other subjects? This is the term exam only. Huh? All the term exams. That means the questions from 5 chapters. Right? Wonderful, right? I will select up some questions and we will do the questions tomorrow as an online. Okay. Like Arafat said, do you need a revision of first and second chapters? Equipped revision. Take your notes. Take your notes. School note here. Everything is okay. Photos are okay. There will not be much of this. Okay, then what is the important one in first chapter and second chapter? Important ideas in first chapter and second chapter. Yeah, derivations are important and equations also. What is the most important thing that is from starting from the first chapter? Yeah, charging is not that important. You just have to understand what is that. That will be enough for that. Charging is not that important. Properties of charge is important. There may be some questions about the properties of charge. You know that properties of charge. I think the idea is very simple. Electric diaphragm. Okay. Properties of charges are additive property, quantization of charge, like charges repel and unlike charges attract, like that. And there is charging, Coulomb's law. When you are okay with the Coulomb's law, right? Okay. Then electric field. I think you are okay with electric field also, right? Electric field E is equal to F by Q, Newton per meter. You are okay with electric field. Then electric dipole. What about electric dipole? Electric dipole. And the derivation part. What about the derivation part? Are you okay with the derivation part with the dipole? We will try it. We will try it. Do you need the electric field at a point P due to the dipole? First one, electric dipole has two derivations. Two derivations. Right? Two derivations. You have two derivations in electric dipole. What is the first one? Electric field at axial point. Electric field at axial point, that is very simple. Electric field at axial point, I'll quickly show that. Electric field at axial point. Axial point. Electric field at axial point. Now this is a dipole. This is a dipole. This is minus Q and this is plus Q. This is a dipole. Okay. The distance between the dipole is taken as 2a for our convenience. And this is the axis. This is the axis. Okay. This is the axis. So I am taking a point here and that point is P. Now, every measurement has to be taken from the midpoint. Every measurement has to be taken from the midpoint of the dipole. So I am taking the measurements from the midpoint. And what is this measurement? That is R. The measurement is what? The measurement is R. Okay. Just look at it. Look at the figure. At P, there will be electric field due to this plus Q and minus Q. What will be the electric field due to plus Q at P? The electric field due to this plus Q will be away from it. That will be away from it. So this is E1. That will be away from it. And electric field due to minus Q will be towards it. So that will be minus Q like this. So a minus E or E2 in opposite direction. Okay. And you can write the equation for E1 and E2. What is the equation for E1? What is the equation for E1? 1 by 4 pi epsilon naught. Charge by distance square. Charge by distance square. E1 is produced by positive charge. So Q divided by distance square. What is the distance? The whole distance is R, but from Q to P, it's R minus A. Right? Here you have A, here you have A also. So the total distance is R, and the distance from Q to P is R minus A. Right? That will be R minus A. That will be R minus A. Did you get it? R minus A, the whole square. R minus A, the whole square. Yeah, for positive charge. For positive charge, that will be Q divided by R minus A, the whole square, right? Okay. And this is a vector. Electric field is a vector. So you have to represent that as a vector. And what is the direction of dipole moment? Dipole moment is always from minus Q to plus Q. Dipole moment is always from minus Q to plus Q. That is, the direction of dipole moment is like this, towards the right. Now, this E1 is towards the right. So, this is in the direction of dipole moment. You can represent that with the P cap. P cap is a unit vector. What is P cap? P cap is a unit vector in the direction of dipole moment. And what is E2? You can write the equation for E2. What is the equation for E2? 1 by 4 pi epsilon naught Q divided by, this is Q minus Q. E2 is the electric field due to this minus Q. And you have to measure the distance. The distance from the midpoint to P is R and R plus A. R plus A will give you the distance from minus Q to the P. So R plus A whole square. And the direction is opposite to the direction of dipole moment. So you can represent that with a minus P. You can represent that with a minus P cap. And E1 is E2 there. And we know the idea that at a point, if you have more than one electric field, you can add them to find the total electric field. Total electric field or net electric field at a point will be the vector sum of all the electric fields due to individual charges. So net electric field E will be vector sum of E1 and E2. Vector sum of E1 and E2. What is E1? E1 is this one. 1 by 4 by epsilon naught Q divided by R minus A the whole square plus and P cap. P cap plus E2. E2 is what? E2 is 1 by 4 by epsilon naught Q divided by R plus A the whole square. This is what? Minus P cap. Right? And this minus will be coming here. And 1 by 4 by epsilon naught Q is a common term. So you can take out that 2 by 4 by epsilon naught can be taken out. If you are taking it out, you will be left with what? You will have 1 by R minus A the whole square here. And the P is also common. If you are applying this minus here, that will be minus 1 by R plus A the whole square inside the bracket. And P cap is a common term, so you have to take it out. Now the P cap. You can cross multiply it, and to find answer, you have to cross multiply it. Net electric field E will be Q by 4 pi epsilon naught is here. Inside the bracket, you have to cross multiply them. That will be R plus A the whole square, R plus A the whole square, minus R minus A the whole square, divided by A plus B into A minus B 2 times. A plus B into A minus B is A square minus B square. So that will be R plus A into R minus A will be A square minus B square. But 2 times. 2 times, no, 2 times R minus R square minus A square into R square minus A square. Right? So that's the whole square. That's why there is a whole square. This is what? This is 2 times R plus A into R minus A. R plus A into R minus A. Once will be R square minus A square. R plus A into R minus A again will be R square minus A square. So that will be R square minus A square, the whole square. And P cap. Now the net electric field has this equation Q by 4 pi epsilon naught. Inside the bracket, you can expand it. This is R square plus 2AR plus A square minus, inside the bracket, R square minus 2AR plus A square divided by R square minus A square. Okay. And what will happen here? 2 by 4 pi epsilon naught. Now this R square and minus R square will be gone. R square and minus R square will be gone. R square and minus R square will be gone. R square and minus R square is gone. A square and minus A square will be gone. This minus into minus will be plus. So 2AR plus 2AR will be 4AR. That will be 4AR. 4AR divided by R square minus A square the whole square. You will get it. This is net electric field. But you have a 2 into 2. You have to convert this into 2 into 2AR. 2 into 2AR. So that will be Q divided by 4 pi epsilon naught. What is this? 2 into 2AR divided by R square minus A square the whole square. And just look at it. You have a Q2A. What is that? Q2A. Q2A is dipole moment. Q2A is dipole moment. So you can write it the 1 by 4 pi epsilon naught. You have 2 here and P here. P is what? P is Q2A. Q2A. So 2P, there is an R here divided by R square minus A square the whole square. Now imagine an ideal dipole. What is an ideal dipole? What is an ideal dipole? The value A will be very small. The value of A will be very small when compared to the value of R. So you have this equation 1 by 4 pi epsilon naught. What is this? 2PR divided by You can ignore this R. Sorry, A square. A square can be neglected. A square can be neglected. You can neglect this A square. So what is that? That will be R square all raised to 2. R square all raised to 2. What is that?
R raised to
Yeah, that's R raised to 4. R raised to 4. So 1 by 4 by epsilon naught. 2PR divided by R raised to 4. Now you can cut it. You can cut it. R and R square is gone. You will be left with R cube. Then what is the net electric field? What is the equation for net electric field? Equation for net electric field E is equal to what? 1 by 4 pi epsilon naught 2p by r cube. 2p by r cube, and which is in the direction of p cap. What is p cap? That's which vector? Dipole moment. That's our dipole moment. This is our first derivation. This is our first derivation. Did you get it? That's our first derivation. So you are okay with this one? You are okay with this one? Can we look at the next one? Okay. Just Is there any problem? Problem anywhere? Did you understand this one? I think this part is all. Did you get it? This one?
Yeah.
Yeah, then this is just expansion of A plus B whole square and A minus B whole square. Keep the bracket, then you will not get confused. Keep the bracket, you will not get confused. Keep the bracket. Okay? Then expansion will be like this. And if you are giving the minus towards the minus r square, and minus into minus will be plus 2ar, minus into plus will be minus a square. That's why this a square and minus a square is gone, r square and minus r square is gone. 2ar plus 2ar will give you 4ar. Right? So 4ar divided by r square minus a square. No. Is it okay now? What if we are looking at the next one? Next one. What about next one? Yeah, equatorial point. Electric field due to a dipole at equatorial point. Equatorial point. Electric field due to a dipole at equatorial point. How can we do this? I will draw a dipole here. This is our dipole. This is our dipole. Now this is minus q and this is plus q. And this is the distance between the dipole. That's 2a. Right? What is equatorial line? Equatorial line is the line drawn at the center. Line drawn at the center which is perpendicular to the axis. Which is perpendicular to the axis. Now this is the line, equatorial line, called equatorial line. Okay? So I am taking a point on the equatorial line. I am taking a point P on the equatorial line. And I have to draw a length to P. And I can take it as x. I can take it as x. But the x will not be in your equation. X should not be in your equation because I am taking the value of x. Right? Every measurement has to be taken from the midpoint. So that's R. Every measurement has to be taken from the midpoint. That is R. Okay. Now this angle is theta and this angle is also theta. Angle will be equal because that's the midpoint. So this is theta and theta. Got it? And due to this positive charge, there will be an electric field at P. And that electric field will be away from P. Like this. So I am taking it as E1. Right? Right? Due to this minus q, there will also be another electric field at P, and that electric field will be towards the negative charge. That electric field will be towards the negative charge. So that electric field will be taken as E2, and E2 is acting towards the negative charge. E2 is acting towards the negative charge. Okay, okay, Abel, I got it. I got it. Rajagiri. For Rajagiri, maths exam is on Sunday. Okay. Did you understand this one? E1 and E2. Okay. Now let's write the equation for E1 and E2. What is the E1? 1 by 4 pi epsilon naught charge divided by distance square. What is the distance here? That's x. You have to take the x square. How can you find x square? You can take this triangle. Yes, you can take the rectangle to triangle and name it as ABP. Right? So you have OPB, triangle OPB. From triangle OPB, you can find the value of x square. This is hypotenuse square. What is hypotenuse square? Hypotenuse square will be a square plus r square, base square plus vertical square. That's hypotenuse square. So x square is a square plus a square, r square. You can take the value here. You can write the value here. A square plus r square. A square plus r square will be x square. And it is acting along BP. It is acting along BP. Along BP. Right? It is acting along BP. What is this? This is acting along BP. Okay. Then E2. Write the equation for E2.
Is P in subscript or
No, BP. They are points. I have shown the position vector here. So that's both are BP. Both are capital letters. BP. And E2. E2 is what? E2 will be 1 by 4 pi epsilon naught charge divided by distance square. That will be same. X is same here, right? So charge divided by distance square will be a square plus r square again. Got it? And it is along PA. It is along PA. It is along PA.
so minus P?
No. It is along PA. If you are taking minus P, then there will be another vector along P to some other term. It is not like that. They are not equal and opposite. Right? They are at an angle between each other.
So sir, BP should be
No. They are not. If there is an angle like, if there is a vector like this, right? That's E1. If E2 is like this, you can take it as negative. Right? It is not like that. It is not like that. It is acting in an angle like this. So you cannot take it negative. You have to take the vector sum. Right? You have to take the vector sum. Okay? Then look at it. This is our E2, equation E2. This is our equation E2. Now you have E1 and E2. And I am redrawing the figure. Here I have the point P. Here I have the point P. If I am bisecting the point P, I will get two angles here. Because this is theta and theta. These are inside angles of a triangle. When you are adding the inside angles of a triangle, you will get the outside angle. So the whole outside angle will be 2 theta. If you are bisecting them, that will be theta here and theta here. So I will redraw the figure. You have E1 in this direction, E1 in this direction, E2 in this direction, E2 in this direction, and the angle between them is theta here and theta here. Did you understand that? Yeah. Theta plus theta will be 2 theta. So the whole angle will be 2 theta. If you are bisecting them, theta plus theta. Okay? Okay? And I am drawing the y-axis also. I am drawing the y-axis also. I will get two vectors. I will get two vectors. One vector here. That's from P to this point. And one vector here. From P to this point. One vector, another vector here. Another vector here. So this is one. The vector that is close to theta is component cos theta. So this will be E1 cos theta. This will be E1 cos theta. And this will be E2 cos theta. E2 cos theta because That's a vector component of E2 that's in the direction of in the same direction. Then that will be even cos theta and e cos theta. Did you understand that? And the vector which is not close to theta will be sin theta. So this will be E1 sin theta. This will be E1 sin theta, and this will be E2 sin theta. Okay. Now look at E1 sin theta and E2 sin theta. They are equal and opposite. They will be cancelled, right? E1 sin theta and E2 sin theta are E1 sin theta and E2 sin theta are equal and opposite. They will be cancelled. Cancelled. They will be cancelled. That means the net electric field will be what? Net electric field. Net electric field will be just the vector sum of E1 and E2. Net vector sum of E1 and E2. What is vector sum of E1 and E2? This one. I will take the magnitude only. I will take the magnitude only. E is equal to E1 cos theta. E1 cos theta plus E2 cos theta, right? Plus E2 cos theta, but E1 is equal to E2 in magnitude. E1 is equal to E2 in magnitude, right? E1 and E2 are same in magnitude, not direction. E1 and E2 are same in magnitude.
Again, even cos theta.
Yeah, again E1 cos theta, again E1 cos theta. So this will be 2E1 cos theta. 2E1 cos theta. That's our net electric field. You can find net electric field like this. Net electric field E will be equal to, what is this? 2 into E1. What is E1? E1 is 1 by 4 pi epsilon naught Q divided by A square plus R square. This is E1. Cos theta. What is the value of cos theta? I will find cos theta here. What is the value of cos theta? From this triangle, you can find the value of cos theta. Adjacent side by hypotenuse. That will be A divided by X. That's A divided by X. Cos theta is equal to A divided by X. What is X? This is X square, right? This is X square. Then X will be square root of this. A square plus X R square. A square plus R square. And square root can be written as A square plus R square all raised to 1 by 2. That's square root. That's square root. So that will be A divided by A square plus R square all raised to 1 by 2. Okay? And what is this? E is equal to, here you have a 2QA, that's P. So 1 by 4 pi epsilon naught. P is on top divided by, what is this? A square plus R square all raised to 1 into A square plus R square all raised to 1 by 2. 1 plus 1 by 2. What is that? 3. Yeah, 1 plus 1 by 2 will be 3 by 2. So that is A square plus R square all raised to 3 by 2. Right? All raised to 3 by 2. Now this is it. This is our equation. A is equal to 1 by 4 pi epsilon naught. And if R is very much greater than A, if R is very much greater than A, you can ignore this A square. You can ignore this A square. If you are ignoring this A square, you will get P divided by R square all raised to 3 by 2. What is R square all raised to 3 by 2? 2 into
R cube.
3 by 2 will be gone. 2 into 3 by 2. 2 will be gone. That means R cube. So P by R cube. P by R cube. This is our net electric field. This is our net electric field, and this net electric field is in the direction of towards the left. It is acting towards the left. And what is the direction of dipole moment? Dipole moment is always from minus q to plus q. Right? Dipole moment is always from minus q to plus q. Did you understand that? Dipole moment is always from minus q to plus q. And this is acting from right to left. This is from left to right. That means this is in opposite direction of electric dipole moment. So you have to take minus p. You have to take minus p. then this will be represented as a vector. Then that will be represented as a vector. So the vector E, net electric field will be what? Net electric field will be minus 1 by 4 pi minus 1 by 4 pi epsilon naught P divided by R cube P cap. This is our electric field. This is our net electric field. Okay? And you can take it as equatorial electric field. E equatorial. What is the relation between axial electric field and equatorial electric field? In equatorial electric field, you have a minus, right? You have a minus equatorial electric field. And there is a 2 in axial equation. So you have to make this equation. If you are giving a minus sign here, this minus sign will be gone. If you are multiplying 2 with equatorial, you will get E axial. Because in the equation of E axial, there will be a 2. In the equation of E axial, there will be a 2. So E axial will be equal to minus 2 into equatorial. Right? This is the relation that is showing E axial, the relation between E axial and E equatorial. E axial and E equatorial. Did you get it? Is there anything that I should be revising?
Electric dipole.
Electric dipole?
In uniform electric field.
Torque. Yeah.
Is that what?
That's torque. Electric dipole in uniform electric field means the equation for torque, right? That's the equation for torque. The final equation is torque equation, right? That's a very simple one. That's a very simple, right?
Next, electric flux. Yeah, P.
Yeah, tau is equal to P cross P. This one. Tau is equal to P cross E.
So you can skip.
Is that okay? Okay. Then anything else? Electric flux is okay. Gauss's law is okay. Yeah. Gauss's law. You need 3 derivations in Gauss's law.
Application.
Is that okay or should I revise it? Yeah, okay. No problem. What is Gauss's law? First, you need to understand what is Gauss's law. What was Gauss's law? Gauss's law. Gauss's law is talking about a net electric flux out of a closed surface.
So you can go a bit fast because I remember.
Yeah. Then what about it? Gauss's law. I can skip Gauss's law.
Go a bit fast.
Okay. Gauss's law is what is it? Phi, that's electric flux, is equal to 1 by epsilon naught times charge in Gauss. That's Gauss. You can prove Gauss's law. I'm skipping the proof of Gauss's law. Is that okay? I'm directly getting into applications of Gauss's law. The first application. What is the first application? You can find the straight line. Straight line. Straight line. If this is our straight line and the current is passing through that line, I am taking a point here. So I have to imagine a Gaussian surface in the form of a cylinder there. We have to imagine the Gaussian surface in the form of a cylinder there. And that cylinder is containing that point B. And you can imagine there is a small surface area here. That small surface area is ds. And there is a Newton area vector. And that area vector will be perpendicular to the surface. That area vector can be taken as ds. Right? It is perpendicular to the surface always. And this line is no, there is no current here, right? The line is containing positive charge. This is the charge distribution, linear charge distribution. So due to this current, there will be an electric field at this point also. There will be an electric field at this point also. This is the electric field. Now the electric field and area vector has the angle between them as 0, and cos 0 is 1. So there will be electric flux through that. But if you are taking a point here, the electric field will be in this direction. This is the direction of electric field, and this is what? This is the direction of area vector. This is the direction of area vector, and the angle is 90 degree. If angle is 90 degree, cos 90 is 0. So there will not be any flux through the faces. There will be only flux passing through the curved surface area. Flux only will be passing through the curved surface area because phi has this equation EA cos theta. EA cos theta or EDS cos theta. EDS cos theta. Okay, that's the equation of phi. That's why this cos theta is important. Okay. Now we have to find the flux through the curved surface area. I can use this equation. I can use this equation phi is equal to what? Phi is equal to EDS cos theta or EDS. And this is a small value of phi. This is small value of phi or d phi. If you are selecting ds, that will be d phi. If you want to find if you want to find, you have to integrate it. Closed integral EDS cos theta. Closed integral EDS. Closed integral EDS. This is what you will get. You will get E dot ds. What is E dot ds? E dot ds is EDS cos theta. And what is this? Here cos 0 is 0. So phi is equal to, sorry, cos 0 is 1. So integral E dot ds. EDS cos theta will be just EDS. That will be just EDS. This is our first equation. This is actually E dot ds, and E dot ds is equal to EDS cos theta, and cos theta is 0 here in the curved surface area. So cos 0 is equal to 1. You can write phi is equal to integral EDS. That's our first equation, right? Okay. Then our second equation. What is our second equation? Second equation phi is equal to second equation. You can see the board, right? Second equation phi is equal to cos law. Here you are using cos. That will be u divided by epsilon naught. You can equate them. This is the second equation. If you are equating them, that's integral E ds is equal to q by epsilon naught. Integral E ds is equal to q by epsilon naught. And E is a constant. You can take it out of the integration. Integral ds is equal to q by epsilon naught. And integral ds is what? ds is this small surface. If you are taking integral ds, you will get whole surface area of the curved surface. Yeah. Then whole surface area of curved surface will be 2 pi RL. That's a cylinder. So surface area, curved surface area of the cylinder is 2 pi RL, and E into 2 pi RL. E into 2 pi RL will be q by epsilon. Right? And what is E? E will be q by 2 pi RL epsilon naught. What is this q by L? Q by L is charge by length. That's lambda. That's lambda. Linear charge density. So you can write E is equal to Q by L is lambda. So 1 by or lambda by 2 pi epsilon naught R. This is our equation. This is our equation. Electric field due to a straight current carrying conductor. Okay.
So we can directly do like this. So write the statement that through the top and bottom faces the product equation. In that,
if you are including that, that will be okay. This is a simpler one, in my opinion. We can show it here also.
we can just write a statement and say,
Yeah.
no electric field through the faces.
Yeah. The reason this is my note. This is not my note, right? Yeah. In my note, there was a dialogue here. What was that dialogue? Electric flux is only through curved surface area. So you have to write that also. I didn't write it. Electric flux only through curved surface area means there is no electric flux through any other surfaces. There is no electric flux through face. If you are following my note, you can write it. If you are following school note, you have to do the whole thing. You have to show it also. Or I am showing it here. Cos 90 is 0, so flux is 0. This will be enough. If cos 90 is 0, flux is 0. Okay. If cos theta is 0, cos 0 is 1, and this is 1. This is flux. This is flux now. d5 is equal to E ds cos theta. Okay. Then E dot integral. This is what? This is that thing. This is that thing. If cos 0 is 0, then that is cos 0 is 1. Cos 0 is 1. Then integral E dot ds will be integral EDS without cos theta. Cos 0 is 1. So integral E dot ds will be EDS. Got it? You only stick with only one node. Either my node or school node. Don't mix them. If you are mixing them, you will be missing something. You either stick with school node or mine, which is better, which is easy to you. You can do that. Easy to you can do. Okay. Then what about the second one? Second one. What about second one? What was the second one? A sheet. Sheet. If you are taking a sheet, the sheet will be like this. The sheet will be like this, and this sheet is uniformly charged like this. And I am selecting a point P here and selecting a point P here, and imagine a Gaussian surface including that P. Imagine a Gaussian surface including that P. This is that Gaussian surface in the form of a cylinder. So I am taking electric field and ds. ds is always here perpendicular. So ds will be perpendicular here. Positive charge is here. So electric field is away from positive charge, and that electric field will be like this. So electric field and ds is perpendicular. So 90 degree. If 90 degree, theta is 90 degree. If theta is 90 degree, cos 90 is 0. Cos 90 is 0. If cos 90 is 0, phi is equal to 0. There is no flux. You can simply show that vector. No flux through that. If you are taking a small area ds, the area vector ds will be like this. This is area vector, and electric field will be away from positive charge. So electric field will be like this. And theta is 0. Theta is 0 here. If theta is 0, cos 0 will be 1. That means integral E dot ds will be what? Integral E dot ds will be just EDS. Right? Okay. Then you can write integral EDS. Integral EDS. E dot ds is what? EDS. That's integral EDS, and that's equal to phi. That's equal to phi. Phi is equal to integral EDS. That's our first equation. That's our first equation. And our second equation, phi is equal to q by epsilon naught from the Gauss's law. That's second equation. And you can equate them. That will be EDS is equal to q by epsilon naught. You can equate them. And E is a constant. You can take it out. Integral ds is equal to q by epsilon naught. And what is integral ds? Integral ds is what? Integral ds is a small area here. So if you are integrating it, you will get the whole area. That's A. Yes, that's A. But there is flux through this part also. Yeah, flux through this part also. This is electric field and this is ds. So here you get 1A and here you get 1A. That will be A plus A. The whole area will be A plus A. Integral ds will be 2A. You can use 2A. You can use 2A now. Okay. So E into 2A will be equal to Q by epsilon naught. So E will be Q divided by 2A epsilon naught. What is Q by A? Q by A is surface charge density sigma. So E will be Q by A is sigma by 2 epsilon naught. You have to remember something. It is independent of the distance. Electric field is independent of the distance from the point. Okay? Okay? So this is our equation. This is our equation. Did you understand that E is equal to sigma by 2 epsilon naught? This is of one sheet. If there is two sheets, that will be sigma by epsilon naught. If there is positive sheet and negative sheet close together, then electric field will be E is equal to sigma by epsilon naught. Just E is equal to sigma by epsilon naught. What about the next one? What about the next one?
Charge.
Spherical shell. Spherical shell. If this spherical shell is charged like this, and we are taking a point here B. If you are taking a point here, that point, through that point you can imagine a Gaussian surface like this. Through that point you can imagine a Gaussian surface like this, and there will be a small surface area ds. Through the surface area you can imagine the vector ds, and you can also imagine E. You can also imagine E, and you can use the equation integral E dot ds. Integral E dot ds will be equal to what? That will be integral E ds cos theta. E ds cos theta. Theta is 0 here. Cos 0 is 1 here. So integral E dot ds will be integral E ds cos theta cos 0 1. So that will be integral E ds. And this is what? This is phi. This is phi. So phi no. This is phi plus phi is equal to integral E ds. This is our first equation, and our next equation is phi is equal to q divided by epsilon naught. This is our second equation. Both of them are equal, so you can equate down. Integral E ds is equal to q by epsilon naught, and follow the same pattern. E is out, ds is equal to integral ds is equal to q by epsilon naught. And what is this integral ds? Ds is a small part of this sphere. So integral ds will be the whole surface area of the sphere. Whole surface area of the sphere will be 4 pi r square. So E into 4 pi r square is q by epsilon naught. And E is what? E is, bring this one, that will be 4 pi epsilon naught q by r square. This is equation for E. If R is outside, that's the first case. And the second case is what? If R is equal to capital R. What is capital R? Radius of the sphere. Right? If R is equal to capital R, E will be is equal to 1 by 4 pi epsilon naught q by capital R square. Right? And now you have to consider the third case. What is the third case? The third case is if R is inside. Yeah. If R is inside, this is our sphere, and you are taking R here. So that will be Gaussian surface will be in this shape. This is Gaussian surface. Okay. How can you find it? Integral EDS. Integral EDS. Phi will be integral EDS. That was question. But phi also is equal to q by epsilon naught. What is this q? Q inside a charged sphere. Charge is on the surface, not inside the sphere. So charge inside the sphere will be 0. That means phi is equal to 0. There will not be any electric field. There will not be any electric field. Phi is equal to 0. Then electric field also will be 0. This one. What is the equation? Just use Gauss law only. Just use Gauss law only. Phi is what? Phi is q by epsilon naught, right? Phi is q by epsilon naught. What is the charge inside a sphere? 0. So charge inside a sphere is 0. So phi is 0. If phi is 0, E is 1. Or phi is 1. Phi is integral EDS. Phi is integral EDS. Phi is integral EDS. That means if phi is 0, integral EDS is 0, and E is 0. ds is never 0 because ds will have a value. Integral ds will have a value which is the area. Now, what is that? E will be 0. E is the one which is 0. Okay? Did you understand that? That's our first step. Okay, I have to go to prayers. Can I take a photo of this? I will solve this question. Hi guys, you can leave the session now. You can leave the session, Natasha, Neha, Reham. I'll be setting another online extra session to discuss the numericals of the that's given from school. Numericals given from school. Okay. Thank you. See you.
It's like 4 years or 5 years.